Thank you. Hi. Yes, as Gregor said, I'm going to talk about higher cognition in dynamic field theory. Gregor talked about language, but in fact we have so far tried to stay away from language as much as possible, but you can't get around language in higher cognition, but we try to stay away from that because it's quite a complex field. And well, I'll just show you what we did, and you can judge in how far that is connected with language. So what you might ask yourself is, what is higher cognition? Because it's actually quite a murky term, which you read quite often in many contexts, but nobody really seems to know what exactly that is. And I try to come up with a kind of an informal definition here by just going through the literature and gathering up stuff about that. And you find terms like thinking, reasoning, problem solving, inference, or even insight, which is closely linked to problem solving. But together it seems that an important thing is that you need to manipulate complex information in a controlled way. So it's not simply perception where something comes in a at least in early stages, mainly feed-forward way, but where you have to have control over the manipulation of the information. And by that extract information that is not explicitly present in the input, but which you have to extract first, get out the implicit information. And that mostly happens in an analytical way, by using multi-stage operations. So it's not sufficient to have simple associations, statistical associations for higher cognition. So you have to do something yourself with the stuff you get from the outer world, so to say. So that probably didn't help too much with a concise definition of higher cognition, but maybe you get an idea of what I'm talking about. So, and there are two opposing or alternative views about how cognition or this type of higher cognition might happen in the human nervous system. And what is often regarded as the classical view is that of amodal symbols being manipulated according to some arbitrary rules that need to be pre-specified, as often used in AI, in propositional logic, for example. For example, we can easily compute that, and then we know that the rabbit is actually faster than the snail, because the turtle is faster than the snail and the rabbit is faster than the turtle. And this can be quite powerful in production systems. In ACT-R, for example, uses things like that. But the problem with that is that it's not easy to interface with the outer world or sensory motor systems. And that means these things these symbols of rabbit, turtle, and snail and faster, they don't have semantics themselves. So if we compute that the rabbit is faster than the snail, we know that the rabbit is faster, but we don't know what it means that the rabbit is faster. So unless we have an interface to the sensory motor level, this doesn't help us much in interacting with our environment. And even if we establish an interface with the sensory motor system, the semantics really lie in the patterns, in the activation patterns that are in the sensory motor system, and not in the symbols that might be, if they are there, somewhere upstream of that. And I say rather because it's not even so clear what semantics really mean. But I would tentatively define it as close in structural equivalence to the real world. So the other view, which is actually even much older than what is called the classical view, is grounded cognition. It's older because it was already mentioned by Greek philosophers, but it has gained some visibility in the last decades, 20, 30 years. Famous proponents of that view are, for example, Lawrence Barsalou and George Lakoff. And this view holds that neural representations in the human nervous system actually do capture semantics, and that most processing is really done using patterns of activation that originally arose through sensory motor experience. So the view goes something like you experience some situation or some stimulus, and some sensory motor activation pattern comes up, and this pattern is then stored in some way, recorded in some way, for example by convergence zones, or that Damasio proposed. And when you reason about these things in the absence of these things, these patterns are reinstated by activating these stored representations and projecting them back into a shared sensory motor representational system in which conceptual processing happens. And the important thing is these are overlapping, these are basically the same or largely overlapping systems with the actual sensory motor systems that are active during experience. So, and this inspired, oh no, actually there's another slide. There's a lot of evidence for this grounded view on cognition. Here are just some rather blunt but classical examples that most of you probably know, these mental scanning experiments where they gave people a map to memorize with different locations, like here I think that's a hut and a well and a tree. They had to memorize this map, and after that they asked people to scan in their mind, without the presence of the map, scan in their mind from one location to the other. For example, scan from the hut to the tree. And people did that and had to press a button as soon as they arrived at the respective location. And it was found that the reaction time increases basically linearly with the distance on that map, although it wasn't present. And there's if it's not a structurally equivalent representation to what you see in the real world, there's no reason why you should find this effect. There could be reasons, but that's the interpretation. A similar experiment in a similar vein was done by Yaxley, where they showed their participants sentences. For example, through the fogged goggles, the skier could hardly identify the moose. And this implies a picture or the thought of a moose that is barely visible, like this picture, or the sentence would read, the skier could easily identify the moose, like in this picture. After reading these sentences, or one of these sentences actually, depending on the condition, the participants saw one of those pictures, and then they had to respond whether or not the animal that occurred in the sentence also occurred in the picture. And it was found that they actually responded faster to this picture if the moose was also barely visible in the sentence. Although you would expect, normally you would respond slow because it's less visible. They responded slow because it seemed that the perceptual representation that was built up during reading the sentence in the absence of the picture is in a way structurally equivalent to what you see in perception, and thus primes the actual perceptual image, so you identify the moose quicker after reading that barely visible sentence. Another well-known effect is the SNARK effect, the spatial numerical association of response codes. This effect occurs when people have to respond to single-digit numbers. For example, judge whether they are odd or even. And when these numbers are in the lower part, like 1 to 4, people respond faster with their left hands, while they respond faster with their right hands when the numbers are larger. And this implies that there's some spatially based representation of a number line or something like that. I mean, there are different findings in this direction which show that this also depends on culture and so on, but all these findings still point to a representation of a number line that is not simply a modal, but somehow linked to perceptual or motor space. Okay, so this, of course, inspired us to form our higher cognition line of work, because this idea of grounded cognition actually fits pretty well with dynamic fields, which are naturally structurally equivalent to the outer world, to the sensory surfaces, and thus come with kind of we could say a natural metric. And this metric can maybe be used to, or can be useful to bootstrap what you can do with dynamic fields to higher cognition, because metric is comes along with relations, of course, and relations can be are pretty important in higher cognition as well. So relational cognition is probably one of the most important aspects of higher cognition. So by bootstrapping from these perceptual representations that come with a metric to relational cognition, we thought we might have a shot at trying what we can do with that in the terms of higher cognition. So, and the first step in that direction was made already some years ago by John Lipinski, Sebastian Schneegans, Julia, who sits up there, and Gregor. And that is the spatial language model. And this model can do a number of things, but all are based on extracting relations from sensory input. And because relations are not something which is explicitly in the input, but which you have extract by operations, this is the first example where implicit information is extracted from visual input by using a DFT architecture. I'll go through that model with a few examples. But what it can do is simply extract a spatial relation. For example, when it gets a sentence like "where's the red object relative to the green one," it doesn't process really verbal input, but gets the different components well, in a more mechanistic way. You'll see in a minute. So if it gets the input "where's the red object relative to the green one," it can select all components in the visual input, which is can be real camera input, by spatial attention. Then it can guide attention given a relation, the red object left of the green one. It can select one object based on this description, and it can even select a fitting reference object when it has to describe the position of an object. So by just saying "where's the red object," it can select another object to say, okay, it's left of the red one, for example. So to be clear, what is really what complex operations are really required to extract a relation from simple visual input, we quickly go through these steps, which have been listed by Logan and Sadler. So according to them, assessing a spatial relation like the lime left of the khaki, this thing here is a khaki, by the way, involves 4 main steps. Namely, you have to bind each object to its role. So first we have to select in some way the reference object, the khaki in this instance, and bind it to the representation or to something that signifies that the khaki is now our reference object, because it's not in the khaki itself that it is a reference object. And we have to do the same thing for the target. Then we have to center the reference frame, this is our reference frame, on the reference object, map a spatial term on that centered reference frame, and then assess whether the position of the target object matches that at which the spatial term points. Okay, so these are the basic steps, and these are implemented in the model. The model is made up of the following components. It gets 2D camera input and includes several fields which are defined over 2D space, the image space basically. These are these fields here and these fields. And up to here, this space is in the retinal reference frame. After that, there is a transformation field which is 4-dimensional. You have heard about that in Sebastian's talk about higher dimensional fields, I think. So you use, I think you have heard about this, right? I mean, in 1D space you can use a 2-dimensional field to transform input to an object-centered frame by projecting it down diagonally. It's just for a reminder, and it works simply the same way in two-dimensional space, only that you need a four-dimensional field, and it's somewhat harder to imagine how that works. These connections here are, with the arrowheads, are excitatory connections, and these with the diamonds at the end are inhibitory ones. So we are in the retinal frame here. These two fields project here. The reference frame is transformed to an object-centered one, and down here are several nodes that implement the spatial terms and the semantic patterns that these terms instantiate in the fields. So going through these steps that are necessary to ground a spatial relation, we have to bind objects to roles, and the fields that subserve this role are the target field and the reference field. These are basically spatial working memory fields, in which each of which one spatial position can be stored. So we basically bind the target object and the reference object to their roles by storing their location in the visual input in these fields. So this is binding via space, as in many of our DFT architectures. So this is consistent with most of the other architectures. The centering of the frame on the reference object is done by the transformation field, as I just explained. And the spatial term or the spatial template is mapped on that frame by these spatial relation nodes. These have pattern connections into the object-centered field. And the object-centered field through that connection is centered on the reference object. So the reference object, you can imagine, it is here, would be here in the middle of the object-centered field. And the semantic weights instantiate a pattern like this one in this field. So if there's a target object up here, for example, above the reference object, it coincides with that pattern. And by matching these two, this target peak and the spatial pattern, we can say whether or not it is a good fit for the position, for the spatial term that is active here. I'll go through that in a little more detail, so don't worry. Okay, so these are matched, and it's checked whether these coincide. Okay. So here's an example, spatial term selection. So the statement here would be, where's the green object relative to the red object, green object, red object. So the model has to select a term that is adequately describes the position of the green object relative to this one. And this works in the following way. First, this dynamic node, which is basically a zero-dimensional field, you have heard about that as well, I think, is manually activated from outside the system and homogeneously boosts this field. This field, I think I didn't explain this, these three fields are color fields. These get input from the camera image, and this input only holds the red objects. This image only holds the green ones, and this the blue ones. So these are basically slices out of a three-dimensional color field in a way. And these nodes implement color feature attention. So the green node is boosted, homogeneously boosts the field that subserves the purpose of representing green objects. This peak here comes above threshold and projects down into the target field, which is boosted simultaneously. That is the important part, because through this simultaneous boost, we ensure that the green object is stored in the target field. And this target field, as well as the reference field, is set to hold self-sustained peaks, or rather one self-sustained peak, which won't decay when these boosts are gone. So we have bound our target position and thus our target object to the role of the target. Next, we do the same thing for the reference object. This is the red object, and we simultaneously boost these fields through this projection here. the peak from this field is brought to this field, and as soon as we have these two peaks instantiated in these fields, they are stored there and project down through that through the transformational field into the object-centered field. So basically what is done here is the position of the target is transformed into a reference, into another reference frame, and the parameter for that reference frame transformation is the position of the reference object. So the reference object would be here, and as we see, here's the target object. It is to the right of the middle of the field because it's to the right of the red object. And next we boost, because the target object is in the right part of that field, the spatial relation node for right is somewhat active, and these nodes can have gradual activation. So these are not, these don't generate binary responses, but they are they can be more or less active, and there's also no competition between these nodes. So the pattern of activation in here signifies how well the position of the target object fits to each of these nodes. These, however, need boosts to become active, and they also have inhibition. They inhibit one each other so that only one can become active. And when we boost these, there's choice is forced between these terms, and we see, okay, the green object is to the right of the red reference object. And this also works for object positions that don't fit so well for the right term. For example, if this object would be somewhere here or somewhere here, it would still probably generate right response, although this is, if there's noise in the model, it's somewhat probabilistic. So that was a simple task, and they actually compared that to what humans do in such a situation. This is data from Regier and Carlson. They showed their participants a rectangle in the middle of a picture, and around this rectangle somewhere a smaller rectangle. And people had to judge on a scale from 0 to 9 how well the position of the second smaller rectangle fitted different terms like above, left, right, and below. The second smaller rectangle always was in positions of a 5 times 5 grid, which the participants of course did see. And so what they got out of this is a table like this one here, where they have average ratings for the different positions. They use different forms of reference object. For example, this table here is for a tall rectangle, and this is for a wide rectangle. The ratings differ somewhat, but we can see this is example is for the above term, and the data in the parentheses is for humans. We can see that the ratings for the above term are of course higher above the rectangle and get lower as we move to the sides, and are very low below it naturally. And it's similar for the wide one, just a little different. And the values not in parentheses are from the model. What these are is the activation of these spatial term node in response of different target positions in the test data, scaled up to the scale that was used by Regier and Carlson. And we can see, if we compare the parentheses values to the other ones, that these fit pretty well. They of course compared that for the other terms as well, and it mimics human data quite nicely. And a more complex task is of course when they're specified only a target object, and we have to find out what we can use to describe the position of the target object. For example, like the question, where's the green object in this example? First, as before, we bind the green object to the target role by applying simultaneous boosts. After that, the task diverges from the first one in that the spatial relation nodes are boosted to achieve that all spatial patterns that the model knows are projected into the object-centered field. These are the four templates for below, above, left and right. And the object-centered field is boosted at the same time. And through that, and the target that projects down here, and the dynamic interplay of the slightly visible positions of the potential reference objects here, a peak will build in this field at the best fitting position for this target object, the potential reference objects that are in this field, and the all known spatial terms. So peak is built here, and this is then, when it is fully built, projects back through this projection to the reference field. A position is selected there, and we can, if we want, read out the color of the reference object then. So in this case, we force a decision by boosting all the color nodes and by boosting all the spatial term nodes, and get out of it that the blue object, that the green object is actually left of the blue object, and that is correct. This was also compared to human data, this time data by Carlson and Hill. And Carlson and Hill showed their participants pictures with 2 or 3 objects. And there was also always one very salient object. For example, it was very large. And this object was always the reference object. It is shown here, labeled R. And then there was another object which was a pre-specified target. This is labeled L here in these pictures. These are different conditions, and people just had to name a relation for the target object. For example, they had to say the target is, and in this case most people would say, or actually all people would say, the target is above, something like that. Or here they would, apparently most people also said the target is above. For example, in this condition, there was a distractor, and this distractor was equally salient as the target object. So this object labeled R here is much more salient than the distractor because it's larger. And now there is the question whether people use the salient object as the reference object, or whether they use a distractor that is a better fit for some other relation with the target object. And it turns out that there's a trade-off, or it's about the balance between saliency of an object and the goodness of fit with some term. For example, here the term left would fit very well when using D as a target object, while the term above would fit less well for the reference object, but the reference the object R, sorry, but the object R is more salient here. And in these cases, people always selected the object R because only this object is available here. And in this case, for example, people often actually chose the distractor because of the better fit. Similar for the other cases. So here there's 50-50 chance because the fit is relatively good for the D, but it's far away, and the fit for R is also not that good, but it's more salient, and so people sometimes choose this object, sometimes choose the other. And the model actually does the same thing. So the white bars here are the Carlson and Hill data, and the gray ones are the model data. Yeah, and the reason is that this trade, probably the reason is this trade-off between goodness of fit and saliency. So overall, we can say we have a pretty general and flexible model, which is quite similar in spirit to the attentional vector sum model, which most of you probably know, because the attentional vector sum model by Regier and Carlson also builds on population response or population coding as a mechanism, but the spatial language model just presented provides a neural account that can actually be simulated, and that is much more specific than the attentional vector sum model, and still fits most of the data that the attentional vector sum model fits as well. So we can maybe say that we are one step closer to higher cognition, and that we have a first example for a neural mechanism that can extract implicit information out of sensory input, and all this in a modal representation of the substrate, namely the fields that are the basis of that model. So what's missing to get to real higher cognition? Probably a lot. So there's a quite nice review by Jonas and Hummel about the demands of higher cognition, or the things that a model trying to capture higher cognition in humans should have or must have. And they analyze that specifically for relational cognition, and they conclude that roughly there are 3 essential ingredients that any such model must have, and this is conjunctive coding, dynamic binding, and the model needs to specify the relation of these. These 3 things can actually be found in various guises in the literature, sometimes implicitly, sometimes explicitly, but this really seems to be the deal. And to go through this stuff, well, we can look whether our model has these things. So conjunctive coding is actually needed to store the conjunctions of roles and fillers, so the binding of roles and fillers outside of the working system, for example in long-term memory, or while the mechanism that actually computes or processes the sensory information, while this mechanism is at work, we need to store the bindings that are currently not stored in there outside of the system. No matter what form this processing substrate really takes, we in any case have to store the bindings somewhere. We can see that we don't have that in the older spatial language model, because we have to supply the boosts manually in order to bind things to their roles. For example, we have to boost, if you want to bind a green object to the target role, we have to supply a boost to that node and thus to that field, and at the same time we have to supply a boost to the target field. And the fact that we have to do that simultaneously is what ensures binding. While this, if we had a conjunctive coding substrate, we could do this autonomously inside the system. We'll see that later. Okay, so no, we don't have that. Then the next thing, dynamic binding, is about, well, arises from the fact that we need a shared substrate. So if we have multiple things stored in a conjunctive coding-like way, in localist units, for example, we still need some substrate where we put all of them together, integrate them, and can work with them. You basically find some kind of shared substrate in almost all higher cognition models if you really analyze them in that way. So we need that. But in that substrate as well, we have to bind somehow objects to their roles, like to the target or to the reference. And so we can say, yeah, we actually, oh, sorry, so we don't have the next thing. We can say, okay, we have that because we simply use space, the spatial position of objects, to bind them to their roles. So that's a nice thing. So we can actually say, yeah, we are one step closer to higher cognition with that model here. And we, of course, didn't specify the relation of these. This wasn't possible because we didn't have conjunctive coding. But of course, if we have a system that does conjunctive coding and another subsystem where dynamic binding and processing happens, we need to say how stuff gets from one to the other while the role filler binding is preserved. Okay, so we set out to correct these no's. We meaning mainly Mattis and me, and Sebastian still works with that, and Julia as well, and Gregor, of course. There's one paper of that out there. It's a proceedings paper from the recent CogSci. And what we did was, okay, we thought about how we could achieve things like conjunctive coding and specify the relation between these two things. We introduced a system of localist units to do the conjunctive coding stuff. and specified the relation of these two systems, so how we get from here to there, by adding a layer of neural organization that is akin to what Mattis talked about in his behavioral organization task. So it's the same principles as used by both Mattis and by Julia in her, or similar principles as used by Julia in her older paper. Okay, and this relation between these two is basically how we can control the different processing steps that are needed in order to do this in an orderly fashion. Okay, so this is what the model now looks like. It's in color, and what it can currently do is, well, basically all that the old model could do. It can ground spatial relations, that is select the components of a spatial relation by means of attention, and it can also respond to different kinds of questions, like where's the red object relative to the green one, or simply where's the red object, and so on. And I'll go through the components of the model. So this is the node architecture which is made up of localist units. This is the system that does the conjunctive coding and is used for controlling what happens in these fields together with these additional nodes here. So these are, as in the old model, dynamic nodes, essentially zero-dimensional fields. And each of these pairs of nodes stands for one conjunction of some concept or some spatial term or color and a role. So we have three roles here: spatial term, reference, and target. And each of these pairs stands for one combination of these things. So for example, if the term above takes the role of spatial term in some spatial utterance or in some spatial relational statement, we store that in this node here. This is a memory node. It is self-sustained when activated, so we can just put it, activate it, and it will stay activated the whole time. And these other purple nodes here are the production nodes. Each memory node has one, and only these are used to pass down the activation from the memory nodes to the grounded substrate here. And that happens when a production node gets input from both its associated memory node and one of the nodes up here. So only when these two inputs coincide on a production node is the stuff that is stored in memory brought to the grounded substrate. Okay, so that's the purpose of these nodes. Currently, there's in this picture there's the spatial relation that is encoded is a green reference object, a red target object, and left off. That is a green object left of a red object. Is that correct? No, the other way around. A red object left of a green object, right? For example, this one here. Okay, this is basically the spatial language kernel that you already know from the old model. These things here are the spatial transformation fields, which are here implemented as convolutions just to make processing a little faster. And we still have a reference field, target field, the relational field, and these additional fields are needed to for the neural control. I'll get to that later. Then here we have something that we also had in the older model, just in a different form. This is the 3D field I talked before, of which the three color fields were slices. So what you see here are just some random slices taken out of that three-dimensional field, which is defined over 2 dimensions of image space and 1 dimension of color. And here we have fields that implement feature attention. If I have a peak in here somewhere, for example here in the middle, this can project down along that dimension into that field and select one color. So it sends in a slice of activation, and all objects that are of this color and represented in that perceptual field are selected and brought above threshold. So this is basically equivalent to the color nodes that we had in the old model, only that it's continuous. yeah, and then the model gets real camera input into the perceptual feed, basically a distribution of salient colors. In this case, there's actually this picture represented in this field. It's a little hard to see. These three bumps here are the red objects, the red cups in this picture here, and they are selected. Therefore, they are above threshold and a little larger than the other ones. This here, I think, is this here is the blue object, and that no, this is the blue object, right? And this is the green one. Okay. And these other things that we haven't seen in the older model are for realizing neural control, and we will see how that works in the following example. So we have this scene fed into that field, and we have the phrase "the red item to the left of the green item" encoded in these memory nodes. So as I said, target object red, reference object green, and spatial term left, and we simply encode that into those memory nodes, and after that activate these three intention nodes here all at the same time, and from that onward the model works autonomously, so we don't have to do anything else, and the model will find the correct answer. The task here is to ground all components of that sentence, so to select all involved objects in the spatial phrase. Okay, we have stored them in the memory nodes. We activate all intention nodes, and what happens then is these two nodes here become active, spatial term and reference. You can see that in the curves here, spatial term is blue and reference is green, so they become active due to the boost we give to them. Although the target node also receives that boost, it doesn't become active because of this precondition constraint. You have probably heard about the precondition constraint in Matte's talk. So it's inhibited by that, so it can't become active as long as the precondition node is not itself inhibited by that condition of satisfaction belonging to the reference object. Okay, so these become active. And what this spatial term intention node does is it projects down here into the layer of production nodes, and so the input from the spatial term intention and from this memory node coincides on that production node, and through a pattern connection from that production node into the fields, the spatial term is instantiated in the relational condition of satisfaction field. You can see that here. So time goes in that direction here, from here to there. You can see here how the relational pattern is instantiated in that field. It is still below threshold because there's no other input than the spatial pattern so far. Right. So this field is similar to this one, only that is the condition of dissatisfaction. You've probably heard about that as well. And it receives the same or a negative version of the input this field receives. So everywhere where this spatial term, in this case left off, does not apply, this field is amplified a little. It's not important in that task, but in the next one, which I will show. So keep that in mind. So at the same time, the reference intention node is active and brings this production node over threshold because it receives two inputs. And this node projects, there's one connection, the connection from these production nodes into these fields are not shown, but this green production node projects into the green position in this intention field. This intention field projects a slice of activation into the green area here in that field, so that all green objects are chosen. And at the same time, the reference field is boosted so that that one green object is stored in the reference field. So here the binding happens again. At the same time, the position of the reference object is also stored in that inhibition of return field, which only serves the purpose of preventing that this object is chosen later again. So if we have chosen a reference object and stored in the inhibition of return field, it can't be chosen later when we do other tasks, or we'll see that in the other task as well. Okay, so and as soon as we have a peak standing in that field here, there's a connection from that field back to the condition of satisfaction, which means, or the condition of satisfaction says, okay, I have chosen a reference object or position of a reference object, and so I can go on to try to select a target. This condition of satisfaction inhibits the precondition node. The inhibition of the target intention node goes away, and the target intention node activates this layer of production nodes. The target color is selected here, selected in this field. At the same time, the intention node boosts the target candidate field, which can hold multiple peaks. And because we have a peak here and we have multiple peaks here, this transformation can go to, comes into effect, and the position of the target items is transformed down into the object-centered reference frame into these two fields. Now, if there is a target object in these candidates that fits the spatial term that is selected here in that field, like in this case, namely left of the green object, there will form a peak in that condition of satisfaction field, which basically means, okay, I have found a target object that fits the spatial term with this reference object. And when that happens, the peak is selected here, then this transforms through this transformation field here backwards into the target response field, which can have only one peak. Here it is, and can project back into the perceptual field too, if we want to read out the color again. But we have grounded all items in this sentence. So reference object, target object, and the spatial term. So that is the easy task. Then we have a different task. It's basically the same task. For the model, it's the same phrase, the red item to the left of the green item, only the scene is different. And this leads to problems because there are two potential reference objects. The reference object should be green here, and so we can choose this one or that one. The problem is that when we choose this one, there's no fitting target object, so we've made a mistake and need to do it again. This is where the inhibition of return comes into effect and where the condition of dissatisfaction comes into effect, because the first part of the task works as the task I just showed. So the model selects this object, binds it to the reference role, and then tries to look for eligible target objects. The problem is there's only an object right to the green one and not left to the green one. And what happens then is the peak of the potential target object to the right of the reference object is projected, of course, down into these two fields. But this time a peak comes up in the condition of dissatisfaction. You can see that, let me see, yeah, right there where the small arrow is. So a peak comes up here, and there's a connection from this field, which is not shown in this image, which serves to reset all these nodes so that the task is done all over again. And because we have the inhibition of return, this object cannot be chosen again as a reference object, and we can now go to this object and then see, okay, this is the item pair I'm looking for. So this basically amounts to a simple form of perceptual hypothesis testing. I'm looking at different items, see whether they fit what I expect, and if they don't, I go to the next pair. Yeah.
Sorry. Does it have any limit, like how many items it can test?
Yeah.
Does it have 3 or 5?
Yeah, that's a good question. I mean, that of course depends on the interaction in the inhibition of return field, how this is set up. But humans probably have that limit, and one thing we plan to do with the model is, of course, fit these data, right? So in the end, the model probably will have a limit. I would say currently it's probably like something like 4 or 5, and that's also what I would expect for humans to have. But we have to check that in more detail, of course. But that's right. Yeah. Okay, so to summarize, we have a fully autonomous model. Of course, we don't have the parsing because I said we try to stay away from the linguistic stuff as far as possible to date. Maybe we will probably have to move in that direction more in the future. But from this point on, the model is fully autonomous. We have a functional system here. But the question then is, okay, is that similar to what humans do? We had a first hint with the data fits in the older model. So there is some parallel to what humans do in that model already. And in that newer model, some of the design decisions we made were actually based on human data. For example, there's data about visual search for spatial relations, where people are asked to find the find the green object left of the red one, and there are multiple pairs in the display. Then you see slopes that are similar to conjunction search, to the search for feature conjunctions, which hints that this is really a sequential process and not a parallel one. And so we made the decision to do this in a sequence in the model as well. Similarly, the sequential choice of the reference object and the target object was based on human data. There's data which shows both behaviorally and in EEG attention shifts between the target and reference objects during the analysis of spatial relations. So it's not like you really just select two objects and immediately see what relation they have, but you have to select them sequentially. And the important thing is, although we have discrete nodes, which you might think is somewhat of a reversion to a kind of amodal processing, although we have these discrete nodes, the processing is all done in the grounded substrate. So these nodes themselves still don't have any semantics. The semantics live in the grounded substrates of the fields that are close to the sensory motor level, or in a format that is similar to the sensory motor level. Okay, here's an outlook. The immediate future, it's basically, or essentially no problem at all, I would say, to include more feature dimensions. We already had that in scene representations. Probably Sebastian Schneegans talked about that, because this simply requires to include more of those perceptual fields, and the binding by spatial position of the different items is there anyway, so this is not a big deal. Then the next thing we are probably doing is letting the model describe scenes freely. This can also be compared to human data, so how humans choose reference objects and according to what guidelines they behave in such situations. Then we are currently working on increasing the embodiment of that whole model by simply hooking it up with a robot head that moves around instead of only covert attention shifts, and probably or maybe also a robot arm to include like pointing to different objects based on spatial descriptions. So this is the immediate future. So then in the near future, we plan to do stuff like building mental models. There's a lot of data about how humans do that. When you give them premises like A is to the left of B and B is to the left of C, they build a model in their working memory and can infer new things from that. Like in this case, for example, when we had this and that, they can infer that A is left of C. That also works for more complex cases, of course. And people do different. If you give them after that, give them premises that don't fit the models they previously built in their mind. They have to revise these models, and they do this according to this data by Knauf et al. By following different kinds of guidelines, which we can or which we plan to also try out in our model and see whether there's some correspondence there to human data. So for this, of course, we need spatial working memory in the model. And this, similar to the multiple features, essentially requires that we connect the model with something like a full scene representation that has multiple feature dimensions, and a dedicated working memory, like the scene representations you have probably heard about already. So this is, I would say, basically stuff that that is not too difficult to incorporate in the model, and we have most of the components already. Okay, then an outlook into the future, and the other question is whether it's possible to bootstrap from these simple spatial relations. I mean, up to now these relations are spatial, nothing else. Whether it's possible to bootstrap from these to higher forms of non-spatial cognition, because there are hints that, as I said in the beginning, that relational cognition is really something that is at the core of higher cognition per se. And then there are other hints that say that space is used as something like a canvas dimension in reasoning, where you map other dimensions down to a spatial representational substrate in order to assess the relations in those dimensions on the spatial canvas. So this is something we plan to do with our model in the future. For that, what we have to do is to find a way to map down from other dimensions, from non-spatial representations to this spatial substrate and back, of course. And well, the ultimate goal, of course, is to get to really complex higher cognition with that. And we have a number of working assumptions for that, namely that there's only a rather limited number of basic operations, like the relational ones I just showed, that can be strung together flexibly in order to achieve complex combinations. That there's a relatively limited number of concepts that can be combined using those those basic operations in order to gain compositionality and get up to the representation of more complex episodes or situations. And what is stored are basically only sequences about the control of instantiating the different patterns and combining them using these basic operations. And most things are, according to our working assumptions, of course, composed on demand in working memory. So there's not as much complex storage of information or perceptual information about episodes as is commonly thought, maybe. But these are, of course, only our working assumptions. We'll see how that works out. Okay, thanks.